Hey folks, in this video we're going to talk about the direction of the magnetic field around a straight wire. There's also I have a demonstration video, or a couple of them with straight wires as well, using a compass in those videos to figure out the direction of the magnetic field. So what does it look like on paper? Well, let's say that we have a wire. I'm going to give it some dimension, okay? And let's say positive current is flowing to the right. In other words, that's our conventional current. Now we know better. We know it's actually electrons flowing left, okay? But we'll say, what if we have positive current, okay? Well, it turns out that the magnetic field makes it wraps around the wire. It makes concentric circles around the wire. And in a little bit, we'll talk about the equation for that. There's several different equations for the magnetic field strength. But for now, we're just going to focus on direction. Now, in this case, the field points, and I'll kind of draw it, and behind the wire, the field points up, and then in front of the wire, the field points down like that. So if you want to add those arrows in like so, okay, so that's our magnetic field direction. Okay, so that's our magnetic field. Now, how did I know that? Okay, so here's the rule. Okay, and I'll try to explain this as best I can. So it's called the right-hand rule. And okay, so what I want you to do literally right now is in your left hand, put your pencil in your left hand and have your pencil facing to the right. That'll be our current. Okay. Then you take your right hand and place your hand so that that your thumb is pointing in the direction of the current. So like the pen will be in the palm of your hand basically, and your thumb will be pointing to the right. All right. And then you'll notice that if you curl your fingers curl around the pen. Your fingers represent the magnetic field wrapping around the current. Okay, so your thumb points with the current and your fingers curl around the pen, and that represents those red circles that we've drawn on the page there. So I'll even write this down. So your thumb is equal to the current, and your fingers curl, that equals or represents the direction of the magnetic field. Okay. Now, we've kind of drawn a 3D view of this here. We can draw a 2D view of this. So we've got current flowing to the right. What we draw is above the wire, the magnetic fields the circles are popping out of the page at us. So we draw dots. Okay. And it turns out that the field will get weaker as you get farther from the wire. So it'll kind of look like that. So that's the magnetic field, and that points out of the page. And when you're below the wire, the magnetic field points into the page. So that's a B, and that's into the page. So dots represent out of the page. Sometimes you'll see circles instead of dots. And then X's represent into the page. And again, I mentioned this before, but dots imagine that you're looking at an actual arrow, like a bow and arrow. The dot represents the tip of the arrow coming toward you. And then the X's represent the fletches, the back of the feathers of the arrow going away from you. Okay. So that's how you determine the direction of the magnetic field of a wire. Now, if you have negative current flowing, like let's say you look at electron flow, well, then you use your left hand. So you'll just get the opposite answer that we got for positive current. So up here you'd have a field pointing into the page, and down here you'd have a field pointing out of the page. Okay, so that would be your magnetic field. Okay. Oh, and then I guess we'll give this a name. We'll call this right-hand rule number 1 for magnetic fields. There's going to be a second one later. Okay, but for now we'll call that right-hand rule number 1. Now you can have the wire have all kinds of shapes. So like in my intro video, I kind of had a wire shaped like that. Okay, so what would happen is if you use your thumb pointing in that general direction, your fingers point out of the page here, and it would look like that, and then your fingers kind of curl into the page below this wire, so it would kind of look like that. So that would be your magnetic field for that wire. Okay. You can even talk about individual charges. Let's say you got an alpha particle. That's 2 positives and 2 neutrons. Okay, it's a helium nucleus. And let's say it's moving that way. Well, that's like a positive current moving to the right. And so that positive charge would make a field looking like this. Okay, so that would be your magnetic field, and it'd be X's down below. That's the magnetic field pointing into the page. So even an individual charge, as it moves, it makes a field around it. Okay, a magnetic field around it. So now, in addition to that, I'll mention this here. I'll wrap it up with this. That charge also makes an electric field around it. Okay, so you might recall it's a positive charge, so the electric field will point outward like so. So it turns out that the magnetic field and the electric field are related to each other. We'll talk about that later. Okay, but it turns out that they're related to each other. One kind of creates the other and vice versa. All right, in the next video, we'll start doing some math and figuring out how to calculate the strength of magnetic fields for different shapes of wires. Okay. All right, look forward to seeing you next one, and have a good one.